Hi, welcome back to the YouTube channel. Today we'll be looking at trigonometry for Math AA higher level. So trigonometry all depends on the circle called the unit circle. And the unit circle is just a circle in the xy plane, so the normal coordinate axis, that has a radius of 1. So it passes through the points 1, 0, 0, 1, negative 1, 0, and 0, negative 1 at these four places as shown. Right? And so the angles that we have here are what define trigonometry. So let's take a look at this. For instance, if we go pi by 6 radians from right here, from 0 degrees, if we go pi by 6 radians, we end up at 30 degrees. And the point that we get here is root 3 by 2, comma 1 by 2. Now, this is the x-coordinate and this is the y-coordinate, and these represent very important things in trigonometry. So the x-coordinate is actually equal to the cosine of that function, and the y-coordinate is equal to the sine of that angle. So in this instance, cosine of pi by 6 is root 3 by 2, and sine of pi by 6 is 1/2. So now if we pick another random angle, say 7 pi by 6 from the origin, or from 0 here, then our cosine is actually equal to the x-coordinate again, so negative root 3 by 2, and our y-coordinate is equal to negative 1/2. Now, I chose this 7 pi by 6 for a very specific reason. If you look at these values here and these values here, you'll see that the absolute value of both numbers, x and y coordinates, are equal, but their signs are changed. And basically what that means is that pi by 6 is the exact same as rotating pi by 6 from pi, which is 7 pi by 6. So pi by 6 and 7 pi by 6 have the same magnitude of rotation, but pi by 6 is from 0 degrees, and 7 pi by 6 is pi by 6 from 180 degrees. So, because it's from the opposite side, it has negative signs. So that's pretty much it. That's how you can figure out any sort of angle based off of the sine and cosine of any sort of angle based off of what it constitutes, right? You find two different angles that add together whose sines and cosines that you know. And that's basically it. So I suggest you only memorize everything from 0 to pi by 2, and the rest is easily derivable. Now let's look at trigonometric ratios. We know that sine theta is the y-coordinate and cos theta is the x-coordinate, but what exactly does that mean? So say we draw a triangle here. So this is the line here, and this is a line here, and this is a line here, and it's a right triangle. So there's a right angle over here. Now, if sine theta is the y-coordinate, that must mean that sine theta also has some geometrical meaning. And to find the y-coordinate, what do? We take the opposite side. So sine theta is opposite divided by hypotenuse, and that's the value of the y-coordinate. Now, cos theta is adjacent divided by hypotenuse, which is the value of the x-coordinate. And that's something you can see right over here. Now, tan theta is something we'll come back to a little bit later, but it's just opposite over adjacent. So if this is opposite and this is adjacent, then this is tan theta. And just do keep in mind Pythagoras' theorem, because that's going to become important once we look at identities. So, here are all the values that you need to know for sine, cos, and tan. Note how tan is not defined at pi by 2, and that's because tan, as we'll see here, is actually just equal to sine theta by cos theta. And so, sine theta by cos theta at pi by 2 is 1 divided by 0. What happens when you try to do 1 divided by 0? Well, it's quite obvious, you can't divide by 0, so we have an undefined for tan pi by 2. So now let's look at their graphical functions. So this right here on the left is sine theta. It passes through 0, 0, so the origin, and it goes up, has a maximum at 1, comes back down to 0, has a minimum at -1, and then comes back to 0, and then repeats the same cycle again. So this right here is a period. Cos theta is very similar, except it starts at the top, comes back down, goes to -1, comes back up, and then goes back to 1. And tan theta is a little bit weird compared to these two. It just ascends forever until infinity, and then at some point, which is pi by 2 to be specific, it just falls back down to negative infinity and comes right back up. So there's a vertical asymptote. And now let's take a look at reciprocal functions. So reciprocal functions are basically 1 over sine, cos, and tan. And there are 3 of them right over here. So the first one is called CSC, and that stands for cosecant. And this is 1 over sine x. And then the second one is called sec, which is secant, and that's 1 over cos x. And the last one is called cot, and that's cotangent, and that's 1 over tan x. So obviously, if we do 1 over sine x, we get sine x, and that means that if we do 1 over cosecant x, we actually get sine x, right? So it's a property that applies both ways. Now let's just take a look at inverse trig functions. So because of the functions that we just defined, we now have 6 inverse trig functions: sine inverse, cos inverse, tan inverse, cot inverse, sec inverse, and cosec inverse. And basically, we only really need to work with the first 3, and that too, that's quite rare. We generally don't work with inverse functions as much for trig. But these functions are also called arc something functions. So the something you just replace with the actual function. So for instance, sine inverse is also called arc sine, and sec inverse is also called arc sec. And this right here is arc sine of x. So it passes through the origin and is defined between 1 and negative 1, and has a maximum value at pi by 2 and a minimum at negative pi by 2. Now cos is just that shifted upward, so it doesn't pass through the origin. This is cos inverse of x. And tan inverse of x is actually defined for all real numbers and once again passes through the origin. So now let's look at some trig identities. So the first one is tan theta equals sine theta by cos theta. So this is the one that actually explains why tan theta here is undefined, because 1 divided by 0 is undefined. Next, we'll take a look at cos square theta by sine square theta equals 1. So Pythagoras' theorem says that a square plus b square is h square, where h is hypotenuse. So we know that a here is the x coordinate and b here is the y coordinate. And we know that sine is the y coordinate and cosine is the x coordinate. So if we substitute sine here, cosine here, and the radius, which is 1 of the unit circle in here, then we get sine square plus cos square equals 1 square, and since 1 square is 1, we actually get sine square plus cos square equals 1. So then that's that identity. It's called the Pythagorean identity. Next, we have sine 2 theta is equal to 2 sine theta cos theta. This is a double angle identity, and you don't really need to know how to prove it. You just need to know that this kind of exists. We'll look a little bit later at that in case you want to do that, but you don't need to know it right now. And cos 2 theta has a very similar identity, which is cos square minus sine square, and that can be written as any of these by using the Pythagorean identity. So, these are some further identities. So this is obviously the 2 that I showed you earlier with the reciprocal functions. So I won't go over them again. Now there's a Pythagorean identity for tan theta and sec theta, which is 1 plus tan square theta equals sec square theta, which is the same as sec square minus tan square equals 1. And similarly for cot and cosec, it exists as well. Now there's an identity here, sine a plus b is equal to sine a cos b plus cos a sine b. And there's a similar one for cos, which is cos a plus b equals cos a cos b minus sine a sine b. So what this upside down plus minus means is that if there's a plus here between a and b, then it's a minus, and if it's a minus between a and b, then it's a plus. So yeah, this is actually how you prove this double angle identity from here. You can use either one. So sine 2 theta would just be sine theta plus theta, which expands to this, and then you can simplify. But it's not really something that you'd need to do on an exam, I don't think. And then tan a plus or minus b again has a similar identity here, and tan 2 theta also has a double angle identity. So now let's take a look at an exam question on trigonometry that might be tricky. I'll give you a couple of seconds to look at this, pause the video if you need some extra time, and then I'll walk you through the solution. So the question says, let theta be an obtuse angle such that sine theta equals 3 by 5. Find the value of tan theta. Okay, so now that you've hopefully had a chance to go through the question, we'll try and do it ourselves. So the first step is sketching a triangle with sides 3 and 5. So we know that sine theta is 3 by 5. That means the opposite must be 3 and the hypotenuse must be 5. So let's draw that out. So this is our right triangle here with an opposite of 3 and a hypotenuse of 5. So now if we use either cos square theta equals 1 minus sine square theta or the Pythagorean identity, Pythagorean theorem, we know that the missing side here must be 4 because 3 square plus 4 square equals 5 square, right? And if this missing side over here is 4, that means that cos theta is actually equal to 4 by 5. But keep in mind, because of the unit circle, cos theta can actually equal negative 4 by 5 as well because it has an opposite here. So the value could just change in terms of direction but not in terms of magnitude. So it can equal negative 4 by 5 as well. And we know that the angle is obtuse. So obtuse means it isn't contained in this positive quarter. It means it's bigger than 180 degrees. So it's actually somewhere in this negative quarter where cos theta is negative. So what that means is our missing cos theta is negative 4 by 5. So if we do sine theta by cos theta, we get 3 by 5 divided by negative 4 by 5, which is the exact same as negative 3 by 4. I hope you found this video on trigonometry and trigonometric functions helpful. If you do have any questions, let me know down in the comments below and I'll do my best to answer them. Thank you so much for watching.